Before we proceed with unequal load sharing, let's revisit the situation we discussed today. At this moment, the routing entry for 10.10.3.0 above has a metric value of 131072. The routing entry for 10.10.3.0 below has a metric value of 130816. We should choose the lower root entry from R3 as optimal and submit it to the routing table. For R1, the route through R3 next address 1.1.13.3. No problem. Next, let's discuss the EIGRP query mechanism. EIGRP query mechanism. So, when EIGRP loses the successor route in the routing table following the loss of a successor route, if there is no feasible successor route available, what next? As a backup, how can we quickly converge, such as switching paths or removing route entries? This is done using the EIGRP query mechanism. Take note, the trigger and operation of the EIGRP query mechanism depend on whether I have a successor route. If I have a successor route, then there is no need to query. If we have a successor route, another successor path that is loop-free and reachable, why query again to converge? Just submit it directly to the routing table. No need to query, since I already have a backup link. Just submit it to the routing table for forwarding. But without a successor route as a backup, we only have one best route, like the current situation. For R1, I have no successor route, only one best path. Another path does not meet the feasible successor route conditions. It cannot serve as a backup route for me. So, if I lose the successor route, and there is no feasible successor, how can I achieve rapid convergence? This is our query mechanism. So, the EIGRP query mechanism is divided into three major steps. First, the initial step is during EIGRP convergence. If a router loses an EIGRP successor route during routing, and the database has no feasible successor route, what will we do at this point? Previously, we discussed the types of EIGRP packets, including hello packets, which discover and maintain neighbor relationships. Hello packets discover and maintain neighbor relationships. There are update packets that send routing entry updates and reliability acknowledgments, ASAKK. Regarding the update packets, they respond, indicating that we have received your routing entry update. Today, we will introduce a new packet type, called a query packet. Query packets are used when the successor route is lost or becomes unreachable. They inquire about related routing entry information to achieve rapid convergence. Once our router loses the successor route, we will immediately, once it's lost, the successor route, and there's no FS, I misspoke, no feasible successor route, immediately inform all EIGRP neighbors. All EIGRP neighbors send query messages to inquire about the routing status to achieve convergence. At this point, if the first scenario occurs, for instance, if the router loses the successor route and the database does not have a feasible successor route, what will we do? We will send query messages to all EIGRP neighbors. This is when the first scenario occurs. If neighbors receive the query message, they will immediately reply with an ACK message. Following this, they check the status of this route. If the neighboring router also does not have information about this route, it will directly reply with a reply message. Students, here comes another packet, called the reply message. So the reply seems simple. When receiving a query message inquires about the status of the route, then if there are results to the query, it is responded to with a reply message. Effectively, use the reply message to respond to the query message. But before sending such a reply message, there will be an ACK. This ACK is simple, as we discussed ACK messages before, responding to RBA packets, so actually the ACK can also respond to query messages, acknowledging that your request or query message has been received. I will immediately begin to check this route. Inquiring about this route, our ACK message not only can confirm update packets, but can also confirm query messages. So once our neighbor router also lacks information about this router, it will reply with a reply message. When a router receives the reply message, indicating that even the neighbor does not have detailed information, it's evident that the route is unreachable. Without detailed information, we know the route is inaccessible, and directly remove the routing entry from the database. Students, this is our EIGRP, thus, the first scenario for querying route entries. Its purpose is quite simple. For example, at this moment, R3 has not announced to R1 the October 3rd 10, 024th's route anymore. R3 tells R1, thus, this 10.10.2-3.0/24 route entry is no longer available. Students, our route entry was provided by R3. R3 informs us this route is now unreachable. This route no longer exists. At this moment, R1 is concerned what to do if this route is unreachable. I also don't have a feasible successor backup path. Should I delete this route or not? Is this route still usable or not? These are the issues R1 needs to consider. So it will send a query. It will send queries to all routers, asking whether this route is still reachable, whether it is still accessible. So for the neighbors, their response will determine whether R1 keeps this route or switches to another path. So the first scenario we just mentioned is based on our neighbor routers, who also do not have this route. So now, to achieve this scenario, we need to use a tool to reach what we are seeing, this kind of query message mechanism, how its query mechanism converges this phenomenon. In the first case, we need to master a way to filter route entries. In EIGRP, the method to filter routes, we will talk about a very simple tool called a distribution list, distributed list. The distribution list is simple to introduce, mainly used in distance vector dynamic routing protocols for filtering announced route entries. So take note, students primarily used in distance vector dynamic routing protocols, and in fact, in what we'll learn later, link state dynamic routing protocols, including their BGP path vector routing protocols, we can use distribution lists to filter route entries. This tool is very useful, and we will encounter it frequently in our future studies. So students must master it. Its main purpose is when we need to announce route entries, when announcing route entries, when we need to announce route entries, during the announcement of route entries, filter the announced route entries. Now let's create a scenario. What scenario? In the first case, suppose R1 loses a route and sends a query message, and the neighbor router also has no relevant route entry information. What should be done? Here's what we do. First, on R2, at this moment we can directly receive from R3 the EIGRP route entries announced to us. And after R3 informs R1, R1 will also announce this EIGRP route entry to us on R2. For R2, I can learn from these two directions of announcements about the October 3rd 10, 024th's route. Next, we need to ensure that R2 does not receive any routes announced by R1 or R3. Let R2 lose this route entry. When R2 no longer has this route, we then disconnect R3, making R3 also not announce this route to R1. 10.10.3.0 route entry. When R1 also loses this route, we will initiate the query mechanism to inquire from the neighbors about the details of this route. At this moment, R2 will have no information about this route entry. See, during this process, R1's query message and our ACK reply message parameters, related packets, we will capture and analyze later. Students, first, let's talk about how to use our distribution list to filter routes. The distribution list in EIGRP looks like this. On R2, router EIGRP 90 distribute list. It can be used for access control or for prefix lists as well. But we haven't discussed prefix lists yet. We'll cover those when we do the comprehensive EIGRP lab later. We'll talk about prefix lists then. Today, let's use access control lists to match routes, using our distribution list to filter. First, our requirements for R2 are simple. We want R2 to receive no information about the 10.10.3.0 route entry. So we need to write a distribution list, write an access control list. Next on R2, say standard access control list, number 1. We do not want to receive any routes for 10.10.3.0. So what do? Deny. We do not want routes for 10.10.3.0. Don't forget, the access control list. For the routes we provide, we have defined its operation, set this regulation to prohibit this route entry. Access control lists come with a deny any by default, meaning for routes you haven't specified. What operation should be taken for other route entries? Our access control lists are default deny. You haven't told us whether other routes should be allowed in or denied. So our access control lists are deny any by default. We need to tell it. So for other route entries, you let them in. Now this access control list, number 1. Its content is very simple. For the 10.10.3.0 route entry. Do not announce it coming in. For other route entries, you announce them coming in. This is our setting standard access control list. We do the route entry matching. Prohibit, allow, we can use the distribution list on R2. Targets your access control list for invocation. Distribute list 1 targets route entries within access control list 1. When you want to announce something, we can invoke it in the outgoing direction or in the incoming direction. For the route entries announced to me, I filter them for you. For the route entries I announce out, I filter them for you. So for R2, this is actually very simple. For the route entries announced to me by R3, including the 10.10.3.0 route, I reject them. Other routes I can accept in the incoming direction from, say, interface serial 0/1, serial 0/1 interface. When I, R2, receive route entries from interface serial 0/1, invoke access control list 1 for the 10.10.3.0 route entry, I don't want it. Let other routes come in. So now, for R2, in my current routing table, I no longer receive the route entries announced by R3 from interface serial 0/1. I route to 10.10.3.0 via R1. Now R2 will only select R1's route entry as optimal because there's no path on the right side. This route entry has been filtered out by me. Then go show IP, EIGRP topology. All links, then only remains hold on a second. The test didn't succeed. Clear, it succeeded. Only the route entry related to R1 remains. Go through R1, so there's no other path. Students, next, we will also prevent R2 from accepting the 10.10.3.0 route announced to us by R1 on R2. Router EIGRP 90, distribute list E in G0, 0 receiving route entries from interface 0, 0 concerning 10.10.3.0. We don't want it. We accept other routes. This is our section list. We match routes with our access control list, using our distribution list to filter in this way. This is how we use routing protocols in the distance to filter routes simply, using distribution lists to filter. So now, for R2, I will now lose all information about the 10.10.3.0 route entry. There is no 10.10.3.0 EIGRP database entry. Next, R1. Currently, we still have show IP EIGRP topology. We can still receive from R3 from interface 0. 3. The route announced to us. 10.10.3.0 via R3. All right, students, what will happen next? We will do an experiment. For EIGRP convergence, if R1 at this moment, we implement a policy on R3. When R3 no longer announces the 10.10, 3.0-R4 route, we eliminate this route entry. R3 no longer gives this route entry to R1. For R1, I will immediately lose my only successor route. The only route will be lost. Then, without a successor or backup, I will immediately send to all neighbors a query packet. I will also send a query to R3. The destination address will be our EIGRP multicast address 224.0.0.10 to ask, then about this lost route. The 10.10.3.0 route entry. So, do you have any clues? Can this route entry still be used? Can it still forward? Then, the neighbor router 802.1x failed. Why do you ask about 802.1x here? We haven't covered 802.1x yet. Now you ask, how should I respond? During overtime, no worries. The teacher is with you. If you work overtime, I'm here with you, don't worry. So we sent out a query mechanism, inquiring about route entries from neighbors. The neighbors would immediately reply with an ACK. It's like what? Like when a leader assigns you a task, then you go and ask me about the situation with the 10.10.3.0 route. You definitely can't tell the teacher, you definitely can't tell the leader that you won't do this task, I quit. What you can do is first agree to it, isn't it? First agree and reply with an ACK. We just talked about how an ACK can confirm a query message. So when you come to ask me, you come to inquire about the route information, what do I first do? First agree to it, first reply back. Then I go look, I go check. What will R2 do? After replying with the ACK, it goes to check the route information. For R2, now I also don't have the 10.10.3.0 route. R2 also doesn't have the route entry. We'll directly reply with a reply, indicating that it also doesn't have any information about the route entry. So R1 finds out that this path tells me there's no route entry. R2 tells me it also doesn't have the route entry. For R1, when I lose this 10.10.3.0 route entry, I have no other paths to access this route now. They all tell me this route entry is invalid. So R1 will remove this route entry from the database as quickly as possible from an unusable route entry directly discarded from the database. This is our EIGRP for an unusable route entry, a convergence method, query mechanism. Now let's see if it's as we analyzed. Now on R3, we write such an access control list for this 10.10.3.0 route. We don't use it anymore. Access list 1.9.10.10. 3.0 let permit any allow other routes. We don't announce the 10.10.3.0 route entry. Announce other route entries. In R3's EIGRP 90, we distribute lists in announcing route entries. When we announce route entries from interface 0, 3 at the time, invoke our defense control list number 1. Do not announce the 10.10.3.0 route entry. Announce data for other routes. So next, we start packet capturing. Capture a packet at R1's 0 interface. Capture a packet at R1's 3 interface. This is R1's 0, this is R1's 3. Then, students. Once R3 stops providing the 10.10.3.0 route entry, it will send an update packet. This update packet about updating the route entry tells R1 this, 10.10.3.0 entry is not available. Let R1 converge. So immediately, we set up this distribution list. The 10.10.3.0 entry is not available. We, R3, will tell R1. So the question is, how do I tell R1 this entry is not available? Look at this packet type. Immediately, then R3 sends an update packet immediately. How does he tell R1 that this route entry is no longer available? Look at this update, announcing route entries. 13.1 and 13.1 say this route entry is incorrect, only announcing one route entry. 10.3, 0, hold on a second. What is he saying now? He's saying now he only has 1.192.168.23.0/24 route entry. No 10.10.3.0 route entry. Students, R3 says now he only has 1192.168.23.0 route. No 10.1.0.3.0 route entry anymore. So R1 says, okay, I understand, comes back with an ACK. Now R1 knows that right now, right here, R3 tells me he only has one route now. Other routes are gone. I immediately do one thing, he queried. Because now I don't know what's the situation with the 10.13 entry. I sent out a query message. So who did I send it to? To 224. 0.10 to all my EIGRP neighbors. Not only to R3, but also to R1 and our R2. All sent query messages. Then, when neighbor routers receive the query message, they first confirm. The first thing they do is to confirm. What do I confirm? You sent a query message. Circuit number I take ACK exactly equal to 65 for confirmation, meaning the query message you sent, I received it. Then after receiving, you see first, for R2, inside this router, R2, I absolutely do not have any information related to this route entry because we previously filtered through the distribution list, making R2's database have no entry related to this route. There's simply no route at all. So when you ask me about this route entry, it's pointless because I also don't have this route. So when R2 replies with an ACK and I check and also don't have this route, the ACK I reply. You see, the reply message you see, he tells you the 10.10.3.1 route entry. You see why R2 would mention this route entry. What does it say here? Look at the wide metric values. Look at the metric value information of the route entry. He says the metric value of the route entry. What's the delay? Infinity. And when is 0? The delay is infinite. Bandwidth 0, hop count 0, MTU 0, load 0, reliability 0, all zeros. It's simple. Inside R2's reply message, I tell R1 that I absolutely do not have any information about this entry. The delay is infinite. I absolutely cannot reach this 10.10.3.1 route. R2 is simply saying that. So R1 replies with an ACK. Okay, I understand now. So this path cannot reach this March 1st 10 route entry, cannot reach this path, cannot reach this destination. Similarly, R1 will ask R3, what's the situation with this route entry? R3 first replies with an ACK, then says, what does it say? The reply message. The reply says the 10.10.3.0 route entry. I have this route, bandwidth, delay, reliability. But look at what, the load is also there, MTU is also there, how much delay, infinity. So it tells you, R3 tells you, this route entry 10.10.3.0. The delay is infinite. It simply can't be reached. R3 then tells R1 that the route entry can't be reached. You should give up on it. We're informing you about this route entry. Now for R1, I don't have this path anymore. He tells me it can't be reached. R3 tells R1 it can't reach this path. So immediately R1 just deletes this database entry. Directly removed from our database because I know now that all my neighbors can't reach this 10.10.3.0 either. Once this route entry is lost, then it simply can't be reached. I just delete it from the database. Just get rid of it. Now pay attention. Why were there these update packets before? What you need to notice is What are we doing now? We made a strategy. For R3, through update packets, tells R1 that there is no longer a 10.10.3.0 entry. When I delete my own entries, because R3 announced a new batch of root entries, R1 now, after database entries converge, needs to send an update packet back to R3 to synchronize again. Tell me again what route entries you have. You see, I have a 172.16.12.0 root. Tell him again about the root entries I have. I have a 10.10.1.0 root. I have a 172.16.1.0 because my root entries have changed now. I now lost a 10. 3.0 root entry. Send a synchronization message. Then you see R3 also has an ACK. Students, now you see, after such a convergence, we find the query mechanism. First, if neighbors do not have information about routes, this information, then we can remove the route entries from the database the fastest. That way, we can quickly remove route entries from the database. Of course, there are other situations. If we lose the successor route and there's no feasible successor, we send a query message. After the neighbors reply with an ACK and investigate, if a neighbor itself has another path toward this route, then it will reply with a reply message about this route's path information. When the router receives the reply message and discovers the neighbor has another path that can access the destination network, it immediately sets the next hop of this route entry to the next hop, indicated by the reply message. Switch to the path that replied with the reply message. On this router's path, simply put, let's do an experiment. Now let R3 still announce to our R1 this October 10th 30 route entry. We remove the filter, let R3 announce to our R1 this October 10th 30 route now. Then, on R2, we make R2 also remove the filter for the October 10th 30 route entry, so that R2 can receive the route entries coming from R3. At R2, router EIGRP 90, remove distribute list 1 in G01, remove it. Now at R2, show running config session router EIGRP, we choose. We just filtered out R1, filtered out the routes given to us. So we can receive from R3 the routes announced. 10.10.30-24 route. Our next hop points to R3. So for R1, now R1, our October 10th, 30 points towards R3. Now this is the situation. And students, for R1, the left side has no feasible successor routes. There is no feasible successor, students. The following situation arises. R2 has another path. So I have a October 10th, 30 route. The next hop is R3. R1's next hop is also R3. Also, in the absence of a feasible successor route. If at this moment R3 no longer announces to R1 the October 10th 30 route, we no longer announce to R1 the 10.3 route entry. For R1, I've lost my successor route. Send the query mechanism, send a query message, asking for detailed information about the route entry. So for R3, it definitely replies it can't. R3 tells R1 it can't, because I originally filtered it, telling you it's unreachable. But for R2, I have a October 10th 30 entry. The next hop is R3 with another path. R2 can access 10.10.30, comma. R2 is routing, right, students? Then R2 can reply with such a reply message, telling R1 it has another path. Can access the October 10th 30 segment. Now R1 knows the path below is no longer viable, but my neighbor above tells me he can reach October 10th 30. So immediately switch over. We respond immediately to re-encode, converging the 10.10.30-24 to R. Through a query message, a reply message, we can immediately discover another optimal path to the destination segment and submit it to the routing table. Now, let's proceed with the experiment. The packet capture remains the same. Pull it down, still capturing. We utilize our distribution list for filtering to observe the phenomena of this experiment. On R3, we filter out again the October 10th 30 route. Unlike before, where R2 had no route information. Now it does, pointing to R3. We filter on R3, examine the packet content, see R3 tells R1 the route entry is gone, informing you my data, my routing table has no such route entry. R1 immediately sends a query to everyone, the query mechanism, inquiring about the route entry's information. My October 10th 30 route entry is gone. Bandwidth 42949672295. One asks about this October 10th 30 route. Do you have any clue? I'll ask around, sending query messages. This route entry I can't reach anymore. The delay is also infinite. Is it unreachable? Could you please reply? So R1 immediately does what? First responds with an ACK, first saying, okay, I got this task. Hold on a moment. Then I'll start checking. During the query, the engine will check. It discovers I have a path via R3. It then states that I have this route entry. October 10th 30 route, bandwidth, gigabit, with the minimum bandwidth along the way being 1000 megabits. Then pay attention to the units, guys. These are picoseconds. Picoseconds in the reply packet regarding the route entry's delay is in picoseconds. What are picoseconds? What did we calculate earlier? 5010 microseconds. Then there's something called nanoseconds behind microseconds. And then behind nanoseconds, there's something called picoseconds. So microseconds times 1000, 50100000 becomes nanoseconds. Then times another 1000, 50100000 becomes picoseconds, guys. Guys, add 6 zeros. So the delay is 5010 microseconds, guys. R2 tells our R1, buddy, I have this route entry. I can access 10.10.30, comma, and it's not through you. I have another path. So R1 then realizes currently my route is gone, but I can find another way. I have another path to access 10.10.30, comma, so I switch it over there. For R1, show IP EIGRP topology. So I immediately now 10.10.30-24, R2 tells me it can access my next hop towards R2 and submit this route entry to the routing table. So now I have another path to access October 10th 30. Guys, this is our query mechanism, the second case of fast convergence. Now for R1, we have another path to access October 10th 30. Guys, this is our neighbor router. When there's another path available, of course, there's a third situation. Let's take a break for now. Of course, there is also a third situation. Let's take a break for now. Okay, everyone, let's take a short break. During the first half of the lecture, we discussed unequal load balancing, and then we talked about the query mechanism, the first and second scenarios. Let's talk about the process of our query mechanism. So through querying with our ACK and reply messages, we achieve convergence of route entries. If the neighbor router does not have it, then we just delete that entry. If the neighbor router does have it, and luckily has another path, we switch over to it. We thus achieve convergence of the route entry. Of course, all of this is based on not having a feasible successor. Okay, everyone, let's take a break for a while. You can take notes during this time. We will have a 10 to 15 minute break. We will resume at 35 past the hour plus 5. We will resume at 8:40 p.m. At 8:40 p.m. we will continue. At 8:40 p.m. we will continue after the break.